Hi, and thank you for coming to our talk on preparing software engineers to develop robot systems. This work will be presented by myself, Hildebrandt, on behalf of Meriel von Stein, Trey Woodlief, and Sebastian Elbaum. Before we begin, if there's one takeaway from this talk, it's that everything we spoke about today can be found on the class website, which you can access using this QR code or the link shown above. So let's begin. Robotics as a field has grown steadily over the last 2 decades. We now find robots in almost all parts of our lives. We have robots that work in our factories, robots that explore Mars, research robots that can reconfigure on the fly, robotic dogs that can inspect and patrol, robots used to explore cave systems, walking robots that can do acrobatics and dance, drones that deliver packages, swarms of drones used for entertainment and military applications, self-driving cars, underwater robots, teaching robots, and we just watched the first robot fly on another planet. Even with all this, the robotics industry is still projected to grow by 25% between 2020 and 2025. So how are we preparing to fill the need for engineers capable of allowing such development? There are several ways we have been preparing our future software engineers to handle this massive growth in robotics, and each of these approaches generally fit into one of 4 categories. Let's take a look at each individually and see what they focus on and what they are missing. There are specialized graduate level courses that focus on specific elements of the robotic system, such as AI control or mechatronics. These classes tend to overlook the fact that robotics heavily rely on software and the development process to generate that software. In essence, they assume that students are familiar with software engineering principles and can already apply these principles to the system they are working with. Next, there are cyber physical or embedded system courses. These courses are typically aimed at undergraduate students, and these courses generally focus on particular aspects of the robotic system pipeline. However, by focusing on low-level elements of the robotic system, they again miss the opportunity to discuss broader cross-cutting issues that these systems expose. Next, there are massive open online courses. These try to scale up the number of students introduced to these topics, though graduation rates seem to temper that potential. And these massive open online courses fall short in that they aim for a breadth of applicants, meaning that graduates may lack in other fundamental software engineering principles. For example, many of the courses do not call for any computer science prerequisites. And finally, we have traditional software engineering courses. As we know, there are many software engineering courses that are available. However, these courses fail to handle aspects specific to robotic systems. For example, the representation of the environment, more complex definition of state, uncertainty, and noise. And thus, it needs to be taught differently in the context of robotics. So more specifically, what is our goal? Our goal was to develop a course that would enable upper-level undergraduate students to gain expertise on foundational aspects of software development for robotics. Specifically, we wanted to develop a course that introduces students to robotics while reinforcing the principles of software engineering to better prepare students to develop robot systems. So what would be new about our course? Well, we focus specifically on this link between software engineering and robotics. So for example, when we talk about specifications, we are talking about a much richer set of notations for state and timeliness. When we talk about testing, we emphasize the additional component, which is simulation, that is done primarily for robotics. We talk about how uncertainty can be overcome using different software techniques. We describe design patterns, for example, both synchronous and asynchronous behaviors. We discuss code reuse and parameterization. We talk about abstractions, where we emphasize leaky abstractions which occur more frequently in robotics, and we describe how states can be significantly more complex in robotics. However, before we dive into how we incorporated these new elements into the course, let's focus on the challenges that arise when we consider developing such a course. Let's take a look at each of them. First, robotics is a multidisciplinary and rapidly expanding field, so determining the essential elements most relevant to the robotic system development is challenging. Second, there is a constant tension of how to distribute the emphasis between robotics and software engineering topics and practices. Third, software engineering and robotics can be more engaging and effectively taught when applied in practice. Yet the available integrated platforms are specifically designed to handle specific elements of the robotic system. So for example, the Anki Cosmo robot aims to teach control and image processing. Ducky Town aims at teaching image processing, control, as well as swarming behaviors. Thus, there is no available integrated platform that specifically enables experiential learning across both software engineering and robotics. And fourth, typical robotics courses can require significant upfront investment in equipment as well as personnel to maintain those systems once in place. To address these challenges and aid in guiding the design of our course, we came up with a set of core principles. Let's see how they overcome our challenges. The first challenge was a multidisciplinary and rapidly expanding field. These are overcome by principles 1, 2, and 5. First, we prioritize the challenges of robotics that are unique from other computer science systems, which guides which topics to select. Next, we focus on the unique software engineering techniques and practices required by robotic system development. Finally, we reinforce material across both software engineering and robotics. The next challenge was how to distribute the emphasis between robotics and software engineering. These are overcome by principles 1, 2, and 3. We have introduced both principle 1 and 2, so let's take a look at 3. Principle 3 is to provide opportunities for experiential learning to encourage students to practice and reflect on their experiences. The third challenge was that there is currently no available platform. We overcome this with principle 4, which is lowering the adoption barrier by making material more accessible. Finally, robotics courses can require significant upfront investment in equipment. This can also be overcome by lowering the adoption barrier by making material more accessible. Let's look at more specifically how we designed the course using these principles. First, let's look at how these principles guided our selection for lecture topics. We selected lecture topics that showcase the unique challenges of robotics while also focusing on software engineering techniques and practices that aided in the robotic system development. We will discuss how these relate in more detail later on. Next, we introduced the lab component, specifically focusing on experiential learning and lowering the barriers by making the material more accessible. We will again go into more detail about how each of these labs worked later on. Finally, we wanted to reinforce the material across both software engineering and robotics topics. And one way we did that was by pairing the lectures and labs. That way, students would learn about concepts in a lecture and then reinforce these concepts through practice in a lab. Let's look at each of these lecture-lab pairings in more detail. We start with the introduction. The introduction introduces robotics to the class and briefly touches on conceptual models of robotics. The lab introduces ROS, which stands for the Robot Operating System. ROS, despite its name, is not an operating system, but more of a middleware used in robotics, and it is responsible for handling communication between programs in a distributed system. Next, we introduce different development features. Here we compare the traditional development lifecycle used in software engineering with the development lifecycle of a robotic system. This helps contrast and highlight the similarities between both cycles. In the lab, we start introducing them to the drone simulation we'll be using throughout the rest of the course. This simulator is modular, and thus we can present it with varying levels of complexity. To begin, the students can simply pass the drone a waypoint, and the drone will automatically fly to that position. Next, in the lectures, we introduced first how real robotic systems are implemented and how they are modeled. We then introduce how these models can aid in code management. Next, we show students how state machines can be used to manage system complexity. In the labs, we ask the students to use a state machine to safely fly the drone inside a virtual cage. We now move to start focusing on how software engineering principles can be used to solve common robotics problems. One of the most common problems in robotics is the non-deterministic noisy input space. We introduce the students to 3 different ways to handle these issues. First, we focus on calibration, next filtering, and finally sensor fusion. In the labs, we showcase how noisy sensors can affect their drones in real time. This is done by simply enabling new features in the simulator. The students then use what they've learned in class to implement a carbon filter to remove the noise. Next, we introduce students to how perception can be used in robotics to aid in understanding the world around the robot. For the lab, we enable the down-facing camera, increasing the complexity of the simulator. Using the down-facing camera, students can practice different perception algorithms to aid in navigating the drone around the simulation. Now that students are able to get the robot to understand the world around itself, we introduce students to different control schemes. In the lectures, we introduced the students to both open loop and closed loop control schemes. In the lab, they used different controllers to follow a ship around a map. They tuned their controllers to have the drone precisely hold position above the ship. In this lab, we also introduced the students to testing robotic systems. Specifically, we made use of ROS tests, which are similar to unit tests in software engineering. The next two lectures focused on making plans, localization, and navigation. This is again a good example of how our software engineering principles aid in solving these issues, both from an algorithmic perspective and from an implementation perspective, where the choice of algorithm can severely affect the time complexity and responsiveness of the robot, and the data structures used can help in solving these kinds of problems. In the lab, the students tested their knowledge on making maps and plans. Here on the bottom right, you can see the drone making a plan to navigate around a wall, which is represented in blue squares. Finally, we introduced the student to transformations. Transformations are common in robotics, where information might be given in a different frame of reference and needs to be converted into the frame of reference your algorithm or software expects. In the labs, we used an example of how a tower which publishes another robot's position in a different coordinate frame. The students were then tasked with converting the second robot's frame into a frame they could use as input to their code, which used to track a ship. The drone would then follow this new robot around while planning routes around the obstacle in the world. To increase the students' breadth and perspective, two additional issues were focused on during the course. First, the class is aimed at upper-level undergraduate students, and thus many are starting to consider positions in industry. For this reason, we invited a guest speaker from industry to speak and interact with the class. Next, as robotics grows and becomes more apparent in our lives, there will be several ethical questions that will need answering and considering when developing these systems. We added a lab where students would debate over these issues, and as there is no right or wrong answer to many of these ethical questions, the goal was not for the students to find the answer, but rather to expose the students to the complexities of these ethical questions. In retrospect, this class introduces several innovations. Here we list each of the innovations as well as which principles were responsible for these innovations. First, our course was able to cover robotics fundamentals. Our course provided different levels of abstraction, both during lectures where we incrementally increased the complexity of our descriptions, as well as in the practical components where the simulation allows us to incrementally increase the complexity of the simulation by adding different components as the course progresses. We paired software engineering and robotics topics throughout the course, building the students' knowledge in both areas, while using each as a vessel to teach the other. We enabled students to make design and implementation decisions in the lab, allowing students to experience scenarios similar to that of the real world. We made use of demonstration, conversation, and checkpoints as a way to interact with students, enhancing our ability to determine a student's understanding while providing the student with an opportunity to further their learning. We used a simulator which was abstracted from a real system, allowing students to get hands-on experience with designing and implementing robotic systems. We incrementally build on concepts minimizing required background knowledge in robotics while also not overwhelming the students. And we incorporate flexibility into the course by allowing for self-paced labs and adding catch-up days into the design of the course schedule. To get a better sense of the course, let's take a look at both an example of a lecture and a lab. This example lecture is from our Week 3 lecture titled Software Machinery. The aim was to introduce the fundamental concepts related to robotics architecture and modeling machinery and robotics. The lecture begins with the basic conceptual architecture of robotics. We then cover the critical domain-specific architectures. We discuss the design trade-offs over different scenarios. And finally, we introduce a finite state machine and discuss what types of states they can encode, how they can assist in understanding the real world, how they are represented in code, and how to scale them up. Next, let's take a look through an example lab. The lab starts by highlighting what we learned in class can be used to implement real systems. We then ask the students to implement a basic two-state finite state machine. This allows students to start feeling more comfortable with the concept and not become overwhelmed. We then highlight how ROS can be used to debug this information. This allows students to self-debug their finite state machines, making sure it works as intended while learning good debugging principles. We use checkpoints to allow students to reflect as well as discuss what they have done with either one of the instructors or one of the teaching assistants. We then emphasize how certain design attributes should be parameterizable and how students should design code to be easily reusable. With this in mind, we ask the students to add an additional state to their finite state machine to verify the input given to the drone in simulation. The verification is done, again, using parameterizable constraints, allowing students to demonstrate code reuse and flexibility. We then add another checkpoint, allowing students the ability to describe what they've done. And then finally, the students would demonstrate what they've done in the lab, as shown on the bottom left, where you can see a drone flying around using a keyboard. The idea of the project was to give the students a problem which required implementing the techniques taught in class, but also to give the students the freedom to implement their own solution. For this, we decided on the following problem. First, the students would need to read the drone's position from another source, which provides this information in a different frame of reference. Then the drone would need to search a map filled with obstacles and locate an object. Once the drone detected the object, it needed to perform a set maneuver to collect the object, and then it needed to find the quickest path to a safe location where it could drop that object off. Here you can see how this was presented to the students, where obstacles were either static walls shown in yellow or fires which appeared randomly. The object was a dog whose location was random. The drone was given a map of static walls, and the down-facing camera could see both the fires, wall, and dogs. Well, single dog. Let's discuss the lessons learned. Specifically, we wanted to look at what worked well and what needs improvement. Let's start with what worked well. We found that the pairing of software engineering and robotics works well, as it reinforces the students' understanding of both software engineering and robotics concepts. Second, building flexibility into the course was very beneficial, as it allowed us to spend more time on concepts that we found the students to be struggling with during checkpoints and one-on-one discussions. Third, we found that using different levels of abstraction helped students more quickly grasp concepts and allowed them to focus on the material we wanted them to learn, rather than getting lost in an overly complex system. For example, in the labs, we start off with a basic simulation with no noise and no additional sensors, and then we introduce noise, followed by more complex sensors, and finally environments. Fourth, incrementally scaffolding the course material again helped the students focus on what counts, while being able to ignore parts of the work which are not necessary for the concepts we are trying to teach them. Fifth, our team structure of 3 teaching assistants was a key in allowing for discussion and checkpoints where we had time to do one-on-one discussions with the students. Finally, the checkpoints and reflections were key, as it allowed us to identify where students were struggling and guide them to a deeper understanding, while also allowing students that grasp the work more quickly to not feel like they were being slowed down. Similarly, there are several things that need improvement. First, the diversity of students' machines still presents a challenge, as no matter what solution we had, there was always a few students whose computers' configurations just did not support or struggle to run the current simulation. Second, as both robotics and software engineering are continually developing fields, identifying both fundamental robotics topics and matching them to software engineering principles requires additional and continued thought. Third, the checkpoints and discussions do have drawbacks, for example, requiring more time for both grading and discussion. Fourth, as this course builds on software engineering and robotics, we require the students have some understanding and knowledge of programming and basic algorithms. Identifying exactly what prerequisites are appropriate for this course is challenging. Finally, requiring a way to empirically assess this course needs improvement, and we plan to do that in future iterations of this course. Overall, however, we feel like this course was a success. In the future, we aim to empirically test how successful this course was. Last year, we had 26 students. This year, we have 75. Of last year's 26 students, 4 ended up in the robotics industry, despite them having no intention of doing so before the class. Additionally, we had several students who emailed us and thanked us for how they actually used concept learned in the course while talking with companies that ended up hiring them. In conclusion, we introduced a course aimed at equipping students with a unique understanding of the challenges in developing and the software underlying robotic systems, and a set of tools to address those challenges. And with that, please remember that all of this, including the lectures, labs, and simulation, can be found on our class website, which can be accessed using the QR code shown on the left. Thank you very much.